Hello, Stat 300, and this is Professor Gonzalez. And I would like to take a look at some problems from our homework section 11.3, which is hypothesis testing for the difference between two means paired samples. So I think we kind of need to talk about this a little bit before we dive right in here. So I would like to take a look at just some slides here. It says a sample of 8 automobiles were run to determine their mileage. That's in miles per gallon. Then each car was given a tune-up and run again to measure the miles a second time. So as you can see this data chart over here, we've got some pairing going on. We've got automobile number 1. We check the mileage before the tune-up and then the mileage after the tune-up. And the thing about this is that, both of these pieces of data are paired. They came from this automobile. And the same goes true as you go down the list. So that's why we have paired samples. The sample mean mileage was higher after the tune-up. We would like to determine how strong the evidence is that the population mean mileage is higher after the tune-up. Okay, so a couple things going on here. Let's go like this. It said we would like to determine how strong the evidence is that the population, I want to highlight that, the population mean mileage is higher after the tune-up. Well, very often to figure out something about the population is very difficult to check every automobile before and after a tune-up in the population, right? So that population is a very difficult thing to get to. And by the way, if you remember, population mean is, we use the variable mu for that. Now, as I read on, it says these are paired samples because each value before the tune-up is paired with a value from the same car after the tune-up. Something else to notice here is we're trying to find evidence that the population mean mileage is higher after the tune-up. So we're trying to say something about the population, but since we can't check every car in the population, what we do instead is we get a sample. And so these are samples. In fact, you can take a look at the sample. In this case, n is 8. We have 8 samples, right? 8 cars that were sampled. And mu is our population mean, but remember in the past x bar was our sample mean. Now something's going to be a little bit different here because we're going to take a look at the difference of the two pairs. Well, let's move on and we'll see what's going on with that. Let's move on here. Matched pairs. When we have matched pairs samples, the pairs are called matched pairs. By computing the difference between the values in each matched pair, we construct a sample of differences. All right, well, let me read on a little bit and then I'll talk more about that as it pertains to this chart or this table. If we denote the population mean mileage before the tune-up by mu sub 1, okay, that's right there. Now remember, this is the population mean of the automobiles out there in the population before a tune-up, and that's before the tune-up. And then the population mean after the tune-up would be mu sub 2. Then we are interested in the difference, so we want to take the difference of those two population means, one before the tune-up, one after the tune-up. Because these are paired samples, the population mean of the differences we can call our notation the population mean of the differences. Now the population mean of the differences is just going to be the population mean of the cars before the tune-up minus the population mean of the cars after the tune-up. Once again, we don't have the ability usually to survey or talk to each person that owns a car out there and to make these to to get the data for the whole population. So what we do instead is we do a survey. Once again, this is like the last slide, n equals 8. So this is only a survey of 8 automobiles. So therefore, performing a hypothesis test on mu sub d, which is the population mean of the differences, is the same as performing a hypothesis test on the difference of the population means. So let's see. So that's what I put right here. And that's what we're going to be looking at quite a bit of really the whole time with these matched pairs. Let's take a look at notation just to kind of drive that home. We talked about it a little bit, but we need to define some notation and remember some things. Okay, next slide. Let's see, notation and assumptions. We use the following notation. So d bar is now the sample mean of the differences between the values of the matched pairs. So remember our sample mean in the past, x bar was our sample mean. Right, so you sample a bunch of people or whatever, and then you find the mean, add them all up, divide by the number of samples, and we've got our sample mean. That's the same thing as d bar right here. It's just that it's the sample mean for the differences. So if you take all those values right there, 8 values, because these values are what the differences of, so basically subtracted, right? Take the differences, and that yields the differences. I don't know why I feel like I have to do this on every single row. That gives us the differences, and then if you take each one of those differences, add them up, divide by 8, that would give us our d bar, which is the sample mean of the differences. That's what d bar is. Okay, so in this particular section, we don't use x bar. It's still the same thing. It's still the sample mean, and it's still the sample mean from one data set, but it came from the paired samples, and it was the difference of those pairs. Okay, so it's a difference. That's why we use a d. Next variable we're going to look at is s sub d. Now, little s is the sample standard deviation of a sample, right? But this one is just the sample standard deviation of the differences once again. Whoops, lost my pencil. So we've got the sample standard deviation of the differences. Sample standard deviation of the differences. So remember we had a formula for that. You would have to take this value, whoops, what happened? Take this value and subtract it from the standard deviation, the sample standard deviation, and then square it, and then add it to this sample. So we've got a formula, and we'll run through it. And oh, by the way, we also have the ability to use our ALEKS calculator, and that's open on your homework and your test. I'm going to give you, I couldn't actually run the program on here, but I took some screenshots to try to show you. I'll show you how to do it by hand, but when you see how fast the calculator is, you're probably just going to use the calculator on this. But that's okay, because we've already worked on sample standard deviations. We already did that by hand. We also did sample means, and then we did that by hand, so it's okay to use the calculator. What else do we have? Next variable is, and we talked about this one already, this one, whoops, is mu sub d. So this is the population mean of the differences of the matched pairs. Whoops, I keep on losing my pencil for some reason. There we go. So really what that means is when you see this, it means the difference of these the population matched pairs. So the population, let me see if I can say that. The population mean of that first population minus the population mean of that second population. And when you subtract them, you get the population mean of the differences, which is that variable. Okay, that is this population mean of the differences is not a value that's in front of us on this table, because this data really is just samples. It's not the population, it's just pieces of the population, and we're trying to use statistics from this sample to tell us more about the population mean. Okay, some of the assumptions. The method requires the following assumptions: that we have a simple random, whoops, that was great, that we have a simple random sample of the matched pairs, and that either the sample size is large, that would be n, the sample size must be greater than 30, or the differences between the items in the matched pairs shows no strong evidence, shows no evidence of strong skewness or outliers. This is required to be sure that d bar will be approximately normally distributed. So what you do to kind of check this quickly is you can use a dot plot to check, to make sure that we don't have major outliers or extreme skewness. So this is kind of just a quick check. The problems in this particular book, or these particular problems, are not really asking us, there isn't a place to actually do this, but I just wanted to show you that you really should be doing this to make sure that we don't have major outliers when our sample size is smaller than 30 or equal to 30, right? Really want to be greater than 30. And the two problems we're going to do, the sample size is definitely smaller than 30, but we're not going to do this because it just wasn't part of the question, as you'll see in ALEKS. But once again, I wanted you to be aware of this is assumption that's happening. All right, so that takes care of that. Let's go ahead and move on up. What next? Let's start. Do I have anything else? Oh, also wanted to show you that this is our formula sheet for test number 4. And as you can see, it has all this great information here. This particular section we're working on is 11.3, which is a test statistic for the difference between two means matched pairs. That's what we're doing right here. And there is our test statistic, and you can see, what is it? It's a t-value. So when you see that t right there, you know that we're going to have to use the t table or t distribution, right? So it tells you right there. You just have to kind of pay attention to it all. Let's see, can I get rid of that stuff? Oh, it's a little slow. There we go. Okay, so that's what we're working on right now. Let's go on and go for, also within that formula sheet, you also have, right, our normal distribution, z table positive, z table negative. There's our students' t distribution that we'll be using for 11.3, and also our chi-square distribution, I think for 12.1. Okay, let's do this thing here. And let me get a little more space. It says crossover data. Okay, question number 1. A crossover trial is a type of experiment used to compare two drugs. Subjects take one drug for a period of time, then switch to another. The responses of the subjects are then compared using matched pair method. Oops, pencil doesn't work again. Matched pair methods. In an experiment to compare two pain relievers, seven subjects, okay, you can see over here 1 through 7, so that, n equals 7, right? We're just kind of getting some information. 7 subjects took one pain reliever for 2 weeks, then switched to the other. They rated their pain from 1 to 10, and we know 1 is mild pain and 10 is severe pain, with a larger number representing the higher levels of pain. The results are listed below. Can you conclude that the mean pain level is less with drug B? So the way this book deals with when you have 2 pairs of data, they kind of just define one of them for us, which makes it kind of nice. And here it is right here. It says, please let mu sub 1 represent the mean pain value with drug A. That means that mu, so let's use another color. That means that that drug B is going to be with mu sub 2. So let's get our colors down here. Drug B is our green. Drug A is our red. Let's see. I think I want to say something like so. Now remember, this notation is indicating population. And down here, these are samples from that population. So we're trying to say something about a population without actually talking to every single person in the population. So we're trying to talk about the population mean of the differences right here, okay? So they just defined mu sub 1 as what? As drug A. And therefore mu sub 2 must be, must be drug B. So the population mean of the differences of drug A minus drug B is going to be our population mean of the differences, okay? So we kind of have that set. Now, let's see, what are we trying to prove here? Can you, okay, I think I'm going to use some other color. Can you conclude, there it is. Can you conclude that the mean pain level is less with drug B? Okay, well, if drug B, can you conclude that this is less? Well, for that to be less, because pay attention to that subtraction symbol there, right? So if drug B is less, that's going to be, let's say, a larger number minus a smaller number. So if you have a larger number minus a smaller number, that's going to be something that's bigger than 0. Let me say that again. This is kind of a tricky part. It says, can you conclude that the mean pain, can you conclude that the mean pain level is less with drug B? So I know that 11.3 is all about these paired differences. So if drug B is less, that means drug A is larger. And we already know the order of this. It already said, let me use the color, mu sub 1 minus mu sub 2, and we also know that mu sub 1 is drug A. Okay, so we know the order is this in our subtraction problem. Subtraction is not commutative, so you got to make sure, that's the tricky thing. The order is very important as you read this, as you read the words and write your difference. So, so can we conclude that the mean pain level is less with drug B? Well, if this second, right, if this green stuff is less than the red stuff, or let me say it the other way, if you have a number minus a small number, the outcome is always going to be bigger than 0 or greater than 0 or positive, right? So that's what we're trying to conclude. So that is going to be our wrong color. That is going to be our alternate hypothesis, right? Okay, so let's go ahead and write our, see if I can do this over here. Flip the page. Let's go ahead and make the statement of the null. So this null hypothesis is just going to be, and this is going to be this almost the same every single time. Well, really it is the same every single time. We want to know the assumption is that the population mean, or the population mean differences is that there's no difference. So when you subtract the two, you get 0. Okay, so the assumption is that the population mean of the difference is 0. That means both the two values are the same to get 0. The alternate hypothesis said the population mean of the differences, and we said it and we kind of figured it out, worked it out here, is greater than 0. It's greater than 0. Well, if it's greater than 0, what kind of tailed test is this? This is going to be a right-tailed test. Okay. The next thing we need to do is find the critical values. Round your answers to 3 decimal places. Okay, well, to get the critical value, we're going to need, now remember, let's go back over here. Remember that these paired, difference between two paired matched pairs is going to be a t-value. Okay, so why do I say that? Well, because if you're going to find the critical value here, you're going to need to know the n value. And what is that? Our n value, there are 7 subjects so in the sample, so n is 7. Why do I need to know that? Well, because I need to know my degrees of freedom, which is just 7 minus 1. So degrees of freedom is 6. What is the alpha level? So we can figure out our critical value on a rejection region. If we go back to that original problem again, it says that with an alpha level of 0.05. So alpha level of 0.05. Okay, so you got to be really careful here because when you're looking at z values and you're finding critical values and things like that, we have a nice handy dandy chart here that gives us very common significant levels, and I put a note here. This is for z values. So we're talking about t values. You've got to go to that t table. Let me go back and review or remember the pieces of information we need. Okay, we need degrees of freedom are 6, and we need to know that the alpha is 0.05. Now, another thing to be very careful of is that on our t table, unlike the z table, this table gives us area to the right. In fact, they tell us right there, this is area to the right tail. So you got to be careful. If you're doing a left tail t-test, you just have to put a negative sign on that value and put it on the left. If you're doing a two-tailed t-test, you got to be very careful because the area to the right, you're going to have to split that in half because half goes to the right, half goes to the left. So maybe I'll make an example of that after I finish this one, just to kind of show that how that two-tail works. Okay, so let's go back here. What was the? Let's see, I got off track here. Well, that's not too bad off track, but we had degrees of freedom 6 and 0.05. 6 and 0.05. 0.05. Use some color. Degrees of freedom is 6. There we go. Okay, so we have a t-value of 1.943. Where'd that go? Right there. So our critical value is t sub alpha is 1.943. Compute the test statistic, round your answer to 3 decimal places. Okay, we have some work to do. Now I'm going to do this first one by hand, but also show you that we have support with the calculator to do this. And it's going to make things much quicker, but I'll just show some of the work by hand, just so maybe it connects some of the ideas from the past. So some of the things we're going to need for this formula. Let's see, how do I want to do this? Let me go back to this page. Let's write down the formula we're going to need here. The formula that we're going to need is that this is for our test statistic, is we're going to need d bar, which is the sample mean of the differences, minus m naught, which almost always, usually I'll say, usually is 0. And this is all divided by the standard deviation of the differences, and that's divided by the square root of the sample. Make sure you're clean with your calculator work there. So that's the formula that we have to find our test statistic. How did I know that? Because I'm smart? No, because I just copied it right from there. Okay, so it's right there on our notes. Let's come back here. So you can see what is required. We're going to need a, do I want more color here? Sure, I'll use red. We need a d bar. What is d bar? It is a sample mean of the differences. Oh, I meant to erase this so I had more space, and I didn't do that. So just going to have to deal with this. It's going to be kind of close. But what I'm trying to say here is we need the differences. Let me write differences. And what do we define our differences as? Here it is right here. Drug A minus drug B. Drug A minus drug B. Trying to use the right color. Jeez. Drug A minus drug B. And it was subtraction. So our first difference would be 4 minus 1 is 3. 5 minus 5 is 0. Where am I at? 7 minus 6 is 1. 5 minus 3 is 2. 7 minus 2 is 5. 7 minus 3 is 4. 2 minus 1 is 1. So our difference is right here, and I think I want to try to highlight this. In what color? I don't know. I guess we'll use that. Go a little bigger. Those are my differences. Okay. And so 3, 0, 1, 2, 5, 4, 1. So remember that thing, that piece I needed to get my test statistic? Where'd it go? Where'd it go? There it is in red. D bar. Okay, let's find that. If you remember back in the day, chapter 3, sample mean. That's just add up all those values and divide by the total value, and that's going to be the same thing with our d bar. So all we have to do is add up all these differences. 3 plus 0, you can see where I'm getting it from right there. 3 plus 0 plus 1 plus 2 plus 5 plus 4 plus 1. Did I do them all? 3, 0, 1, 2, 5, 4, 1. And then divide by how many pieces of data, my n, which is 7. So when I do this, I get d bar is approximately equal to 2.2857. And that was that red value I was just talking about. Okay. What else do I need? Let's go back to the formula. I'm going to need this sample standard deviation of the differences. If you remember in chapter 3, by the way, these two pieces of information, these two statistics that I'm finding here, this is chapter 3 again. I want the sample standard deviation. Here's the formula, but once again, I'm also going to show you how to do this by using the calculator. Basically, how do you do this is you sum up. Well, first of all, you take the difference of a value, one of the values, a data, a sample point, minus the sample mean, square it, sum all those up, and then divide it by the sample size minus 1, and don't forget to square root it. That is your sample standard deviation. Now, of course, in this particular section, it's the sample standard deviation of the differences, so we use that little d. And here's how you do it. You take, so here's, once again, we're taking a look at our data points right here. Here's our first data point, 3. And then you subtract your standard, or your d-bar. So it's going to be 3 minus, and then you can see there it is, 2.2858, so 57 rather. Then you have to take the difference and square it, and now go for the next one, 0. And then you take 0 minus d-bar, 2.2857, square that, and then go for the next piece of data, 1. 1 minus 2.2857, square it. You're going to do that all the way out to the last one, the last data point, which is 1 minus 2.2857, square that. The formula says divide it by n minus my sample size. There are how many in the sample size? 7. So it'd be 7 minus 1. And that whole value gets square rooted. And so when I look at the standard deviation of the differences, I get approximately 1.7995. And I'm going to circle that. And I think it would have been better if I just circled this one. So those are the two pieces of information that I need. Now let me show you that there's a really fast way that we can get this stuff by, and that is using our ALEKS calculators. That all you have to do is just push the little calculator button in the upper right hand corner, and it looks something like that. What you're going to do, let me put this in a place where you can see what's going on. So all you need to do, now this is for the standard deviation, that's the tougher one. We could also actually get this d-bar. We can get this d-bar really easily by just clicking on an x-bar. That's the same thing as d-bar. It's just that these are differences, right? So once you found the differences right here in yellow, it's just an x-bar, but we call it d-bar, so we know it came from a matched pair of differences, right? So if you just click on this button right here, and then you put in 30125441, make sure to put commas on it, and hit enter, it will give you that value. That wasn't that much of a time saving because you just added up and divided by 7. That was pretty easy. But as you can see, finding the sample standard deviation and then square rooting it down here in green, that is a different story. That's tougher for sure. And so if you wanted to do that in a quick way, all you'd have to do is hit S sub x, which is our sample standard deviation. This guy will come up with a cursor open, and then you plug in the values. 3, 0, 1, 2, 5, 4, 1. Where did that come from? 3, 0, 1, 2, 5, 4, 1. I just plugged in those values. Just make sure you know those aren't ones or something. I just plugged in those values with commas in between. I hit enter or equal sign, and guess what pops up? Let me minimize that one. And this guy then pops up with what number? Well, look at that. Oop, look at that right there. Oh, gosh. I'm trying to be smart here and I can't do it. Stop. There we go. Look at that number right there. Should match up with that number right there. So we rounded to 4 decimal places, approximately 1.7995, 1.79947, so rounds up to 5. Okay, so that was really fast. So I would encourage you to do that because, we really don't want you to make a mistake with the sample standard deviation and then mess up your calculations, because really what we're trying to do is teach you how to do hypothesis testing with matched pairs, okay? And so the standard deviation is just a sub-calculation. You might as well use a calculator and get that thing quickly and correct. So now that we have our bits of information that I just found, and I showed you multiple ways of doing it, by hand or by calculator. Let's do it by calculator, next problem. We've got the t equals our d bar, which happens to be 2.2857. Remember, it's minus 0, so that just goes away. Then down below, we have this quotient, and we have our sample standard deviation, which we end up getting as 1.7995. That is divided by the square root of n, and the sample size is 7. Just make sure that if your calculator is not clear on how you're putting this in, put parentheses in to make sure that that quotient is in the denominator. Once again, I've got all these pieces in here correct. Yes. I hit enter and I get approximately 3.361. So there's my test statistic. So now the next question is, what do we do? Do we reject or do we not reject? And so I think what we need to do is go back. Let's go back to our original statement here and maybe make a little picture for ourselves. So here we are. And remember how we said the assumption is the population mean differences are 0. So there it is, 0. And that's what we're assuming it to be. And then we're going to run it through a statistical test to see if we can, if there's enough information to go with that, or if our test statistic by sampling goes so far off away from that mean that we are forced to reject that null and go with the alternate hypothesis. Now this is a right-tailed test. So we're talking about over here. Let me see, what was a critical value so I can make this picture kind of in line, probably something like that. So this is a right-tailed test, so let's go ahead and show that as a right-tailed test. That critical value that we found somewhere in the problem was 1.943. So once again, you're sampling. With the sampling, you're making this test statistic, and then you're plotting it on this curve somewhere down here, right? And by chance, the differences are probably not going to be 0, meaning the two matched pairs are not going to have the same exact value, probably. Even if the population mean did have that, the differences happen to be exactly 0. By sampling just a portion, small portion of the population, there's a good chance it's not exactly 0, but this is acceptable chance as I sample, acceptable. But once you get a sampling that's out here, that's far away from what we expect the difference to be 0. Once we get out there, We are now going into our reject zone. Remember what caused this rejection zone? Well, because they told us that the alpha was 0.05. And then from that alpha, we looked up what is this t value. Remember, these are t values. What's this t value right there? So now, big drum roll, we want to see what happens. And I think we're going to use, let's use purple on this one. What happens when we take this test statistic and plot it? It turns out that I can't go far enough over here. It turns out, what is it, 3? It's way out here. I mean, it is way out there. It turns out that our test statistic came up approximately at 3.361. This is clearly in the rejection zone. We must reject. What are we going to reject? We must reject HO. So here we are. It says determine whether to reject. Reject. Okay, so we must reject. Now the last bit here, it can get a little bit complicated. I mean, you kind of can wimp out with this thing because it says, I mean, once you're rejecting, now there is enough evidence to support what we're saying. And if you don't reject it, then there's not enough evidence. But, you know, really digging a little deeper to kind of try to understand what's the outcome when you reject. So let's take that a little deeper here, even though you may be able to get the right answer without getting as deep. But let's see. So we said from the beginning that our null hypothesis said that the population mean difference we're assuming is 0, and that the alternate hypothesis said that the population mean difference is greater than 0. Okay, now greater than 0. Now we define this stuff at the very beginning by saying what is m sub d? Well, that is just going to be defined by taking, going back to the language of the first problem, drug A minus drug B. Okay, so now using our test statistic, what did we do? We came through and we said, no, we are going to reject that, which means we have to go with this. So if we have to go with the alternate hypothesis, what's the only way you can have a m sub d be greater than 0? Well, this has to do with subtraction, right? If you subtract a big number from a small number, it's going to be positive. It's going to be greater than 0. If you subtract a small number from a big number, it's going to be negative. It's going to be less than 0. So the fact that we're saying that mu sub d is greater than 0, that must mean that this is bigger or higher, and we're talking about higher pain. So this one has higher, it's a bigger number, so higher pain for drug D, which means this one has lower or less pain. Let's call it lower pain. So really all they wanted to know is there is enough evidence to conclude. But then, this is where we really get into the details that we kind of want here. There is enough evidence to conclude that the mean pain level is less with drug B. And that's what we just said. Yeah, it's lower. That's what that's saying. It's lower. Okay? All right, let's go on to the next one. The next one, we're actually going to use the calculator to go quicker. So I don't have to do it by hand and by calculator, just one or the other. I did kind of promise to take a look at doing a two-tailed test with the t-distribution. Let's kind of take a quick look at that. And that's not really on our list of things here, but I think it's a good thing to kind of go over as that could come up. So, as you know, I don't have a lot of space here. Let's see. So if we have two-tailed, oof, that's pretty sloppy. So if I had a two-tailed test, it basically looks like this. Oh, I'm getting called. I told everybody I am making a video. Still, I get called. Anyways, a two-tailed test is going to look something like this. So if we're looking for critical values and we have this two-tailed test, and let's say we're looking at an alpha level of 0.10, remember when it's a two-tailed test, this area under the curve, and you know, if it was a p test, this red stuff would be the p-value, but right now we're doing critical value, but this area, or this alpha, has to be added together to get, or separated I should say, because it's a two-tailed test. That means if it's separated, that means that this side has half of 0.10, so 0.05, and this side has 0.05 in it. So see how this gets a little more complicated? So if they said they wanted an alpha level of 0.10 and it's a two-tailed test, you have to take half of that at 0.05. You'd go there, and let's just say, let's making this up, let's say that n equals 9. So that means degrees of freedom would be 9 minus 1 is 8. So then if you're trying to figure out the critical value here, you'd go degrees of freedom is 8. And we need to take a look at this guy right here. And that would tell us that this critical value is 1.860 on the upper side, on the right tail, and negative 1.860 on the negative side. So two-tailed test can be a little bit tricky because you have to split the alpha on both sides, and when you're talking about p-values, you're splitting the p-values also. Anyhow, so you got to be careful with that a little bit. Let me move on from this point, and let's do our final problem. Got to clean that up because I'm going to be coming in here to do let's see, where are we at? Number 2, and here it is. Strength of concrete. Okay, strength of concrete. The compressive strength is kilopascals, was measured for concrete blocks from 5 different batches of concrete, both 3 and 6 days after pouring. So I don't know if you know about concrete, but it gets stronger as it cures. That makes sense, kind of like glue. But concrete has all this moisture in it, right? It starts all like a soupy, depends on how much water. It's just supposed to follow the directions there. But anyways, kind of like oatmeal, I guess, right? And so, it's awesome. So you could form it and move it and all these great things. But then as it dries, it's just hard as a rock, right? So it's awesome for construction. But as it dries, it increases in strength. As the water evaporates out of it, it gets stronger and stronger. And it's kind of crazy that it continues to evaporate and release moisture. I think the Hoover Dam is still releasing moisture, which is crazy because that was built so long ago, but there was so much concrete, but that's another story. So let's check out this. It says, so we're looking at the strength both 3 days and 6 days after pouring. The data are as follows. So here's the important stuff. Can you conclude that the mean strength after 3 days is less? Okay, than after 6 days, and that's the key word right there, is less. Okay, the nice thing once again is they're going to do some defining for us. Let's let mu sub 1 represent the mean strength after 3 days. Okay, and we're saying we're defining that our population mean of the differences is going to be mu sub 1, which was the red, minus mu sub 2, which is the green. So if we're trying to just get this to make sense in our brain a little bit in terms of this problem, it would be the population mean of the differences is going to be calculated by taking mu sub 1, which is after 3 days. So I'm going to write it after 3 days. Boy, this is getting really sloppy. After 3 days. Like a third grader here. No, kindergartner. Minus, now I can't even, after 6 days. Okay, so that's kind of keeping in mind what is the population mean of the differences. It's calculated by that difference. So remember, let's do it early on this time, now that we know what we're doing. And I wish once again that I gave this a little more space. I was supposed to do some editing with this, but it didn't happen. Anyways, differences. Let's find our differences. And our differences, once again, is defined over here. After 3 days minus after 6 days. So we just have to do this subtraction problem right here, right? And so I've got 1304 minus 1,319. So this is going to be a negative 15. I take the difference of the next, I get negative 27. Take the difference of the next, I get 4. I get negative 12. And I get negative 6. Okay. I think I'm going to now highlight the differences so I can go back. Remember, those are real important numbers for me to get my d bar and my S sub d, my standard deviation of the differences. Okay, well, what's next? Let's figure out this statement. The first one is really easy because it's always going to be the population mean of the differences. We're going to assume that there's no difference. So if there's no difference and the two values are the same, when you subtract them, you get 0. Then we get this alternate. So we're trying to prove, can you conclude that the mean strength after 3 days is less? Okay. Well, if we're trying to prove that this is less, and that means that this is bigger or greater, let's call it bigger. Not greater because we're talking about days here. Or no, we're talking about strength. We're talking about strength. So let's call this, so that's less, and this is stronger. Or more. I don't know. What's the outcome when we have that situation? Let me just say that again. I feel like it kind of got off a little bit there. What we're trying to prove here is we're trying to say right here in yellow, can you conclude that the mean strength after 3 days is less than the mean strength after 6 days? Can you conclude that the mean strength after 3 days is less? So this one would be less and this one would be more. Well, if you have a, let's call it a small number minus a big number, what do you get? You get a negative number, right? Small number minus a big number, you get a negative number. That means that we need to test for something that's a negative or smaller than 0. Okay? So, that, let me say this again, because this I think is just the tricky part, really, of the whole thing. Because everything else is just hypothesis test again. It's just these are differences, and once you get your differences, that's one data set right there. But you still have to set up, oh, my throat. Anyhow, So let me say this again. It says, can you conclude that the mean strength after 3 days is less than the mean strength after 6 days? So can you conclude that it's less after 3 days, which means it's more after 6 days? That means that this is a small number minus a big number, like how about 4 minus 10? That's going to give us a -6, something that's less than 0. Okay, so see where I'm going with this? I'm going with a sore throat is where I'm going with this. So that gives us our alternate hypothesis. Okay, this is therefore is going to be a left-tailed test. And then we move on. Now we find critical values. We found out that our sample size is only 5. And once again, such a small sample size really should be looking at dot plots to make sure there aren't any major outliers or extremely skewed. There isn't any points for that, or places for that, I should say, so we're going to just let it go. N is 5, so therefore our degrees of freedom is 4. We go back here, and they're asking us to do this at an alpha of 0.10. Alpha 0.10. Okay, so remember those two pieces of information. Degrees of freedom 4, alpha 0.10. Let's go to our table. Degrees of freedom 4, alpha 0.10. Come down, move over. There's our number right there. Now remember, this whole table is all about giving you the area and the right tail over here. So by doing what we just did, we just figured out that at 1.533, the area to the right of that is going to be 0.10. That's with 4 degrees of freedom. Okay, well, what do we have going with our question? Well, our question, if we want to take a quick look at the picture, remember we said this is a left-tailed test. So if we're on here with this left-tailed test, and let me remind you again, we just found, because the way that the table's set up, we just found right to the right. So all you have to do is take that number and put a negative sign on it, and we've got the left-tailed. We've got the critical value for the left-tailed test. So I take that value that I had, that I just got, and I put a negative on it. So negative 1.533. That's our critical value. Now we need our test statistic. And this will go pretty quick because, I do need my differences. And if I go back up here and I take a look at my differences, I can just re-record this down here. So let me rewrite this down here again. On the right spot, yep. So what were my differences? Let me write it here. Differences. Well, we had a -15. We had a -27. We had a 4, a -12, and a -6. And you're just going to put those differences in the calculator. And d bar is now going to be -11.2. And my sample standard deviation of the differences, by plugging these values in there, just like I showed you on the calculator. On the calculator right here, right? All we had to do was select that button right there. It doesn't want to show anything. All we had to do is select that button, and then standard deviation, put those values in, the differences in there with commas, hit enter, and we've got our value already. So that is super nice. Don't want to delete a page. Okay, so now I've got my Sample standard deviation of the differences is approximately 11.4324. Okay, now I go to my table, or my formula, and there is the formula for my test statistic. And it's really not too bad. Well, we did have to find those values, but those values were not bad when we used Alex graphing calculator, or Alex calculator, statistical calculator. So we put in our d bar, which is a negative 11.2 minus 0, so don't worry about that. Divided by my sample standard deviation of the differences, which was 11.4324 divided by the square root of the sample size 5. And I put that in my calculator, and I get a test statistic of approximately negative 2.1906. What does all this mean? Or do I have space to work? Right there. What does all this mean? It means this. It means that when I take a look at my distribution, and I remember that we're assuming that the differences are going to be 0 right there at the population mean, we found a critical value of negative 1.533, critical value of negative 1.533, which then helped us to locate our rejection region. And then we found our test statistic right here in green. And we need to plot that. Now, once again, we expect, we would expect if the population mean had a difference of 0, we would expect just by chance for us to be plotting test statistics from the sampling somewhere in here, right? We'd be okay with that. But we're saying if it goes further than we're okay with, which was the alpha of, I believe it was 0.10, then we're going to reject it. Now, let's go ahead and plot. Drum roll, we're going to plot this, and when we plot it, there it is right there. It's further to the left. Let's say about there. It is negative 2.1906. It's definitely in the reject region. Reject. It's definitely in the reject region. We must reject. Where are we at? This one right here. Reject. Okay, so we just rejected the null. Once again, whenever you reject the null, that means there is enough evidence. If you don't reject the null, there is not enough evidence. Just to kind of break this down, once again, that the details would kind of get tougher. Let's see if we can understand why this sentence says what it does. There is enough evidence to conclude that the mean strength after 3 days is less than the strength after 6 days. How can we make sense of that? Well, we go back to this statement that says a population mean of the differences is going to be, I used red, the strength of concrete after 3 days minus the strength of concrete after 6 days. Now our statement is there, and didn't we reject the null? That leaves us with that statement right there, that the population mean difference is less than 0. That leaves us with this idea that this whole thing is less than 0. That means it's negative, right? Less than 0 or negative. Well, when you have a number minus another number, how is it going to be negative? It's only going to be negative if this number right here is the bigger one. So that means stronger in the case of concrete. Okay, so what did it say? After 3 days is less than, okay, let's see. Enough evidence to conclude that the mean strength after 3 days is less. Okay, well, if the 6 days is the stronger one, that means that the 3 days is the less or the weaker one. So that makes sense. That the strength after 3 days is less. Yes, the strength after 3 days is less. Strength after 6 days is stronger. So you could say kind of the same thing in two different ways in some ways, right? There it is. You probably actually could have gotten that correct without digging deeper, but I think it is a good idea to make sense of the word problems. That's what's the tough part. I hope this helped, and I hope you are all doing great. Continue to study, continue to cruise along, not cruise along, we're actually in the final stretches, and we want to finish strong, finish up any remaining homework out there in the adaptive or the assignment side, non-adaptive, and keep on going. You're going to be happy when you finish with an awesome grade. Take care, and we'll talk to you next time. Bye.